Hello, I'm Candice Makita Moore, and I'm going to speak about making AI greener in imaging. So by that, I mean finding and fixing environmental issues. I'll begin by introducing myself. Then I will speak about our current environmental impact. Then I will move on to some practical tips for creating more ecologically sustainable AI for imaging. And finally, I will share some notes on measuring and quantifying environmental impact. So I'm a researcher, clinician, and software engineer. Over the past years, I've worked in terms of applying AI to clinical imaging, mostly radiology, but also done research in ethics. I'm currently mostly working at the Leiden University Medical Center, and I do several things there. Um, what may be more interesting in terms of my background for this talk is that I worked at the Netherlands Science Center for many years, and I looked at ethics in AI, so I got a sort of broad sense of what was going on in this area. In terms of specific engineering solutions, I learned a lot from Robin Richardson and Jero Kamphausen. They developed some online materials that are still available in terms of green digital skills. So my goal in this talk is something quite different than the online material they have. I want to speak to everyone in the room, whether you're a radiologist, another imaging professional, a researcher, or an engineer. I want to specifically highlight the role of people who are not necessarily going to code. Um, I want everyone to understand why working on environmentally cleaner AI solutions is important and how they can contribute, even if they're not technical at all. So I want to begin now by thinking about our environmental impact generally. And that's quite difficult because you can't really quantify these things in a single indicator. There is the idea of a carbon footprint where you take CO2 and methane and some greenhouse gases and roll them all into carbon dioxide equivalents. So that is one kind of environmental damage. And if we look at some of the more popular algorithms, the environmental damage there could be considered large when compared to, say, the environmental damage of a car. However, that's not really necessarily a problem, right? Because in theory, we could look at this in terms of cost and benefit, or like money. $1 million might be a lot for me, but if it cured a major disease, most of us would be happy, elated. Um, there are a few problems with looking at things in terms of a general cost-benefit ratio. One is technical. Energy and carbon costs can often be hidden or abstracted away. There's also a deeper problem, and that is the problem of distribution. When I think of even problems like global warming, which to some extent affect all of us, it's really clear that some people will be much more affected than others. The image of the leader of Tuvalu addressing the COP26, standing where there was once land in Tuvalu, I think brought this home to the world. So our negative environmental impacts are not at all evenly distributed. At the same time, the benefits we bring from AI solutions cannot be evenly distributed either. I put here a picture of a certain clinic in Ghana. If you change the clothes, it could be Haiti or many other places. What's salient about this picture, if you notice, is that the blood pressure cup isn't plugged onto the wall like it would be at my hospital. And that's because the existing electrical infrastructure, the power grid, is not reliable. And the digital infrastructure is non-existent. So many AI solutions, especially commercial ones, presuppose an existing electrical and digital infrastructure, and therefore they simply won't work for a lot of people. There is a special category of AI algorithms that I do believe are helping everyone. Those would be ones that increase the energy efficiency of our machines, ones that reduce contrast usage. But outside of this category, we're really helping only some people. And the people we're hurting are not the people we're helping. So I believe we have a real problem in terms of the ethics of what we're doing. I spoke about CO2. I want to make an even clearer example in terms of water. Unfortunately, the largest owner of cloud and data centers will not release their water usage statistics. And if you have a search engine, you can figure out who I'm talking about. Some of the other major players like Microsoft and Google do release their water usage statistics. We know these centers are not water neutral. What is also interesting is that you can use several resources, and I've used Data Center Map to make the image here, to look at where these centers are located and where they are being built right now. I'm a citizen of Israel, so I wanted to use the example of Israel in case I got any questions about this. We are a water source scarce country in a water scarce region, and we currently have a lot of water problems. We also, unfortunately, have many of even our own citizens who are not hooked up to the water grid. And this has an uneven distribution in the population. It is mostly the Bedouin Arab population that live in unregistered villages that I am speaking about. If you look in a different area in the occupied territories and look at the Palestinian communities there, it is actually the minority of the residents who are getting running water every day. Yet we cannot seem to stop ourselves from adding more data centers. So I think it shouldn't be hard to imagine that this is not only environmentally damaging, but also socially and politically dangerous. So I chose Israel again because I'm a citizen there. You can find examples of this kind of problem around the world in water scarce regions. Mexico would be a good example where certain people in certain communities are having their very lives devastated by the drying that is associated with some of these data centers as they consume local water resources. So I've talked about CO2, I've talked about water. There are indeed other kinds of environmental damages, but what I think is really useful in terms of looking at environmental damage is to think about it in terms of embodied damage and usage damage. So when I say embodied, I mean all of the damage that happen from the raw material extraction to basically distribution. And then usage damage is the damage we're doing by continuing to run this stuff, continuing to power it, and use our memory and so forth. So the good news is when you look at ICT in general, and this would also be true of radiology AI specifically, we are actually doing a lot of the damage in the use phase, in the usage. So that's great because when I think of embodied damage, I think of it as a sunk cost. I'm not giving back any of my multiple computers. However, if most of the damage is coming from how much memory we use and powering our machines, etc., then we can do something about that. It turns out that how we run our code, where we run it, and on what it's running actually matter a lot. So I have a graphic here from UNCTAD about ICT in general. Radiology AI uses a lot of memory, so I would expect the case there to be even more extreme. And this is actually good news because we can have a big impact. So what do I think the biggest things we should be looking at are in terms of what we can do? Well, code-based development and running, CI/CD and testing, I'll explain what that is, and data storage and processing. So in terms of code-based development, it turns out when you develop and when you run your code matters, because carbon intensity has a large temporal variability. So I will state this in a way that people who are not developing code but using it can understand. If you have an algorithm that does something that does not have to happen at a specific time, like let's say an opportunistic screening algorithm, or an algorithm about non-emergent imaging, or a bunch of research code, that can all be programmed by engineers to run at better and greener times, and you can track it and understand what's going on. So think about when your code and programs are running. It's also true that carbon intensity has a large spatial variability. It matters where you develop your code and where you run it. It might not surprise many people to know that the Scandinavian countries are much less carbon intense than, say, Australia. But what that really means is that running the same exact code on the same exact processors, just using different locations, is going to give you pretty different results in terms of your environmental impact. And those of you in the States might want to know that this is true state by state. So your water consumption and greenhouse gas emissions are going to vary a lot, just depending on which state you're in. And those of you in startups might want to really consider this when you think about where you're locating your developers. Another thing that makes a big difference in terms of power consumption and therefore carbon footprint ultimately is the kind of processors you use. Some processors are just way more efficient than others. And there are many other things that can make a difference, such as the language you use. However, there's a lot of nuance here. I would leave these decisions to software engineers. What I think imaging professionals, and only imaging professionals, really need to do is tell software engineers what the whole point of what they're doing is. So that's important because in terms of how well an algorithm is doing, there's a lot of different metrics anyone can look at. I myself, even though I'm a physician as well, when I have on my engineering hat, I want to look at all the metrics and I want to keep optimizing and keep optimizing. But if I'm building a computer-aided diagnostic triage system, is a bit of an overdiagnosis a problem? Is it so much of a problem that I should spend a month rewriting code over and over, using up who knows how much carbon? Engineers will just keep engineering unless there's some oversight. And I sort of added a cartoon of what I hope every radiologist can do, whether they're at the beginning of a project or during some improvement of it. And that is just tell us what the point is, what the metrics are in terms of how well you want the performance to go, and what's acceptable in terms of performance, because 100% accuracy, for example, is not really going to be possible, just like you wouldn't expect a radiologist to always read every image correctly. In fact, the two issues are related since it has to do with labeling. But anyways, for those of you who are actually going to get your hands dirty in the code, my advice is do not reinvent the wheel. That costs a lot in terms of time, but also in terms of energy. Use template code, kind of pre-written code that's open. Take a look and think about transfer learning, etc. What I've actually seen physicians who want to get their hands dirty in the code do is use large language models. That is a terrible idea for many reasons, not least of which that the code can be pretty awful. But because I'm a realist, I'll point out that large language models differ significantly in their environmental impact. And even if you have the same large language model, you can get a different environmental impact depending on how you prompt it. So you want to pick which one of them you're going to use, and then you want to prompt it in the most specific and concise way possible to get your environmental impact down if you choose to do this. However, I would not turn to a large language model as my first aid. There's plenty of open code out there, and for very basic things, you should be able to find it in many places, including the Carpentries course, Medical Image Processing. I'm one of the authors for that, so just thought I would mention that as an example. But there's plenty of sites with open code you can copy paste from, and you don't have to queue an LLM. Now I want to mention CI/CD and testing. So CI/CD is continuous integration, continuous development, and it's always going to be there in commercial products and any serious project that is making this sort of AI. These are automated pipelines for things like testing and deploying changes to the code. These things can be optimized to work just as well as they would if they were running all the time, but have much lower environmental impact. So your CI/CD should not be like a big chain of dominoes where it just keeps going and going. It should be sequential where earlier steps might stop later steps. For example, if your linting fails, do you want to bother running testing? You can stop running testing on every new push because, hey, who cares about the old code now anyways? And you also have an option as a developer to just retest what failed sometimes. Moving on to data storage. This is one of the big areas for imaging AI in terms of environmental impact. The main point I want to drive home here is that your carbon footprint is not based on how much you're actually using, it's based on how much memory is available. So as a researcher, this is really difficult, especially in the Netherlands where you can get grants for, time on a computer and memory and processing. Don't request 10 times as much memory as you need, just in case. There's some complexity here in terms of the type of memory you have and the state it's in. I'll skip over that and just re-emphasize that you should be judicious in how much memory you request. Another point to be made about data and data storage is that the way you interact with it matter. So some clinicians I've dealt with have said, I don't care, I just want to give you the data, nothing more, and I want to come back and see solutions. So even if you're just going to hand me data, you have choices about what you're going to do. You can do that by clicking on files in a graphical user interface and moving them around one by one, or you can write a bash script. A lot of clinicians probably don't want to write a bash script, but what might be attainable is that they find where their terminal is and they start one-line commands to do things like making folders. Over time, interacting with your computer through a terminal is going to be less environmentally damaging than always using and requesting GUIs. So now, finally, I want to talk about quantifying the problem we're creating. So this is more developed in terms of research code, in my opinion, than commercial solutions. I would point to the paper Carbon Footprint Estimation for Computational Research as a good starting point. And if you just want to remember one tool, I would mention the Green Algorithms online calculator. And there's also a tool for high performance computing there. I made a list of the top 10 things that non-engineers could do or should do individually. If it interests you, just go ahead and take a screenshot. And now for some final notes. Individual choices are not the only ones that matter. I want to mention a few things that I don't think are revolutionary that we could probably do collectively. So in terms of researchers, maybe we should advocate to change grant structure to reward and not penalize environmentally friendly work. So it really shouldn't be a reality that requesting 10 times as much memory as I need actually makes me look like a better researcher because I got a larger grant. Also, we should look to grow things like the Green Disc scheme out of the research area. So the Green Disc is a digital sustainability certification, but it's only for research code. So my final message here is that when building AI or even just using your computer, there are many choices and they all matter in terms of environmental impact. And with that, I'll take any questions or comments. Thank you.